Hello everyone, I am Ashutosh Singh. Let me start by thanking the organizers for giving this opportunity to present my work to this community. Hello. So, I'm a PhD scholar at Ramanujan Institute with Dr. Vacchini in Quantum Information and Computing Lab, and I'll be talking about manipulation of entanglement sudden death in an all-optical setup. So this is a brief outline of my talk. So why do we care to learn about quantum entanglement and its dynamics? So first of all, it's a characteristic trait of quantum mechanics. It's a resource in quantum information processing, and the real world success of any of these tasks depend on the longevity of entanglement. And we all know that entanglement degrades due to the interaction with the environment, and therefore it's important to have some techniques where you have an initial entangled state which is decaying. So can we change the time of disentanglement? So there's the big picture of this talk. So what is entanglement sudden death? So here we'll examine the disentanglement dynamics of two initially entangled qubits due to spontaneous emission. So consider two atomic systems which were initially entangled and later they were put into isolated cavities, and the only interaction that they can have is with their own cavities. So atoms cannot interact with each other nor with the other cavity. So we can write down this evolution of system, which is the two level atoms, and the reservoir, which is the cavity, which are initially at absolute zero temperature and they are in the vacuum state. So we can write the joint evolution of the system plus reservoir as a unitary evolution, and if both are in ground state, G is the levels of the system and 0 is the vacuum state of the cavity, so they will remain there. But if your system is in excited state and your reservoir in ground state, so there is a probability that it will remain there, and with some probability it will decay down with an excitation in the cavity. So we can write down the cross operators by tracing out the degrees of freedom of the reservoir, and this way we get the cross operators which governs the evolution of the system. Under Markov approximation, we have P equal to 1 minus exponential minus gamma t kind of decay. So this is the cross operator of a single qubit. If you are considering the dynamics of two level atoms, then we have to take appropriate tensor products of the single qubit cross operators, and the evolution is given by this equation. So if you do this for an initial state of this kind where we choose a equal to 1 or 0, so in both the cases our initial entanglement is somewhere 0.65, and depending on the value of A, whether it is 0 or 1, it can go to asymptotic decay or it can go to finite time disentanglement, which is known as entanglement sudden death. So what is special about it? We are considering the spontaneous emission as only noise present in the system, and it so happens that if you just consider the decoherence dynamics of a single qubit, it's always asymptotic decay. But on the contrary, if you're considering the decoherence of the non-local correlation, that is entanglement, it can follow asymptotic decay or the sudden death. So this is the difference between the local single qubit decoherence and the non-local decoherence. Okay, so this has been experimentally demonstrated in atomic and photonic systems. Here I'll talk about photonic system. So I was talking about this unitary evolution of system plus reservoir. So here polarization entangled qubits form the system, and two special modes of the reservoir, call it A and bottom one B, form the two levels of the reservoir. So what happens if we start with a initial polarization state H, then it will follow the interferometer. So if you have initial state alpha H plus beta VB, so suppose H polarization was going, it will be just transmitted, it will come this way. This is a half a plate 0 degree, it will do nothing, and it will just go through the spatial mode A, and likewise for the other photon. So this is more like system and reservoir both in ground state. If you have a vertical polarization, it traverses the interferometer in this clockwise sense, and you have a half a plate which changes the polarization from V to cos to theta H plus sin to theta v, and here we can write the evolution like this: Va going to with some probability Va, and plus with some probability it can go to Hb. So this is very similar to what you saw in atomic system, and here P is given by sin square 2 theta. Theta is the orientation of the fast axis, of the half-wave plate with respect to the vertical. So finally, these photons are sent to this interferometer, where amplitude damping channel is mimicked using half-wave plate, and these are coherently recombined at this PVS. And finally, here the modes of the reservoir are traced out at this PVS, and they are sent for quantum state tomography. So from here, one can reconstruct the quantum state and then compute one of the measures of entanglement and see the decoherence dynamics. So you can see the parallel between the two systems, G and E, H and V, 0, 1, A and B, and here probability of the damping is 1 minus exponential minus gamma t, and here sin square 2 theta. Most importantly, here the damping channel parameter is time, which is continuous from 0 to infinity, and here half-wave plate orientation can be changed from 0 to 45 when vertical polarization goes to horizontal. And in this case, at t tend to infinity, if you put an atom in superposition state, finally it comes down to the ground state. So there's a parallel between atomic system and photonic system. So here, time is the natural parameter of the system, and here we are mimicking using half-wave plate. So this experiment was done by this group, and what they found was they took two initial states, and depending on the parameter they choose, beta square greater than alpha square or alpha square greater than beta square, one of these undergo ESD and other goes asymptotic decay. So this solid dotted curves show the theoretical expectation, and these points show the experimentally found results. So clearly, this has been experimentally demonstrated. Now, the proposal is, if we have a system with initial conditions and noise which lead to disentanglement dynamics such that it undergoes ESD, the question is, can we do something during this process so that we can change this dynamics? In particular, can we delay it? So the proposal is, if we can perform a local unity operation on individual qubits which are isolated from each other, so we can apply local NOT operation on one qubit or the other, or on the both qubits. So depending on when we apply, we can hasten this process such that disentanglement happens even before. We can delay this process such that disentanglement happens at later time, and then we can completely avoid the sudden death of entanglement. So this proposal is given by one of our collaborators. So now we are working on the experimental implementation of this proposal. So this is the experimental setup. So what is the idea? You have your two atomic systems, and time is continuously running, and it causing decoherence of the individual qubits. Now what you can do is, you have a stream of photons coming in, so you can introduce a half-wave plate which rotates the polarization, and finally when you trace out the degree of freedom of reservoir, it acts more like an amplitude damping channel. So you have a photon coming in, you apply a half-wave plate angle theta, which acts as an amplitude damping channel, apply a NOT operation by another half-wave plate at 45 degree. So this is the first amplitude damping channel here, and then NOT operation, and followed by another amplitude damping channel here. So system has evolved in noisy environment to some time, and then apply a NOT, suitable intervention, and then you again see the evolution in the presence of noisy environment, and see when does this disentanglement happens. So if you do this, here we have the mathematical treatment of the same. So again, start with the two cross operators, initial state, and then evolve it in the noisy environment. So what you find is this density matrix. I haven't given the elements, just you can write down the cross operator and get the density matrix. So now, depending on what you want to do, whether you want to intervene using NOT operation of both the qubits, or just on the first qubit, or just on second qubit, or you can do nothing. So you apply this unity operation on the two qubits, and then evolution will be given by this, and then you can again mimic the damping channel using cross operators. So the final state will be given by this, and then we can apply the PPT criterion of separability, and you can find out the negativity. These are some analytical results. what it tells is the following. So here I said that if you can apply not operation sufficiently early, and if you apply it later, and if you apply much later, then it causes avoidance, delay, or hastening. So we can give the two times, T0, TA and TB. So T0 is the time corresponding to ESD. TA is the time when hastening delay crossover happens, and TB is the time when delay avoidance crossover happens. So in the parameter of P, I can call it P0, PA, and PB. So this is what is given here. So given initial state, I can write down the probability at P parameter when the ESD happens for a fixed setting of first amplitude damping channel, and then you can write the complete end of entanglement. So the joint evolution of two half-wave plates applied one after another causes complete end of entanglement given by this P and by simple expression mod V by X, where the density matrix is written in this fashion for one of the Bell states. So if you apply the NOT operation in both the qubits, then the hastening delay crossover happens at PA value given by this, and delay avoidance crossover happens at this value. Likewise, for the NOT operation on only one of the qubits, you get these parameters given by these equations. So what you find is the following. So if you start with an initial state where entanglement is given by value 0.4 and damping parameter is along this axis and P prime due to the second half of it along this axis. So if you don't intervene in the process of decoherence, then it happens at value P equal to 0.5, and likewise on this axis. But if you apply NOT operation in between, say on both the qubits, then here disentanglement happens. Disentanglement happens in this region. It happens at P prime equal to 1. So this is more like avoidance of ESD. Same results can also be shown in a 2D fashion, where you can actually see that if I don't apply the NOT operation, the ESD happens at value 0.5. If you apply sufficiently early, you can see that P end happens at equal to 1. That means asymptotic decay. And if you apply little later, it delays, but still at a finite value. So this is delay of ESD. And when the curve dips below the value 0.5, this is more like hastening of ESD. So this solid curve shows for NOT operation on only one of the qubits, and dot curve shows the NOT operation on both the qubits. So likewise here you can choose a different parameters of the density matrix, and you see that you are getting avoidance as well as delay. And here you can see that NOT operation on only one of the qubits gives you avoidance and delay, but NOT operation both the qubits gives only delay. So this is the experimental progress. So we are making this type 1 entangled photon source, and this is the brief outlook of this source, and this is the SPDC ring obtained by type 1 polarization entangled source, and this is the Sagnac interferometer that we'll be finally using for this experiment. We just did this feasibility check to see if, and because the complicated setup imposes condition on the physical size of these optical components, so we just checked with the laser, so it's working fine. So once we have characterized the source, we are set to go perform the experiment. This work was, this is the brief summary. This work was carried out with Dr. Urvashi Sinha and in collaboration with Professor Ravi Rao from LSU and another visiting student in our group, Shiva Pradyumna, who is currently at Inrim, Italy. And currently we are working on this experimental part with Shobhajit Bhar sitting somewhere there, and in guidance of Dr. Urvashi Sinha.
I didn't get how you are applying the NOT gate.
If you have a vertical polarization photon, if you keep a half-wave at 45 degree, it changes the polarization from V to H. So if you have a polarization, initial polarization coming in alpha H plus beta V, if you keep a half-wave at 45 degree, it changes to alpha V plus beta H. There's a sigma X.
Okay, if there are no further questions, let's thank the speaker once again.